This video, this is all about magnetic flux and linkage. Now, obviously this is relevant for anyone studying, I'd say, Key Stage 5 physics or senior school physics. However, the stuff I'm going to be talking to today about is really centered towards the IBHL physics course. We're going to look at the link between field strength and flux density. We're going to identify some variables which can change the amount of flux, and then use an equation for magnetic flux and also for linkage. As ever, I tend to talk quite quickly in these videos. In fact, I think this might be the 300th that I'm going to put on YouTube, and during that time I've talked quickly. That's really to save time, but feel free to hit pause and take notes whenever you need to. Okay, and as ever, please ask any questions if you've got them. I'm very happy to answer them. So let's go for it. Magnetic flux is one of these topics which can appear a little bit abstract to students until we know why we are using it. So I think throughout this video, what I would say is that we're going to define something. You're not going to necessarily be 100% clear why we're doing it. However, when you then learn about electromagnetic induction, it will become very clear. And so it's really important that you have a good grounding in this topic of flux before you move on to that part. So let's just have a look at a couple of images. These are stolen from the Save My Exams site. I think it's a really nice image to show the idea of flux. If we look at the picture here, we've got essentially the same thing in each picture. We've got a coil with cross-sectional area A, but however, the difference is its orientation. It's sitting within a magnetic field shown with B, and on the left-hand side, you can see it's kind of upright. So that surface is perpendicular to the field lines which are passing through it. Now, if we want to use this word flux, and again, remember, we've not really defined this properly, we're just using it, we would say that this is a position of maximum flux. And what do I mean by that? It means that there are lots of field lines passing through that coil. Okay, so an idea to do with flux is really the idea of having lots of field passing through. Now, this is where students get a little bit confused, because field is kind of a concept. It's not something we can hold. It's not something that you can really grasp. And so the idea of it passing through is quite a weird one. Really just is the idea of the orientation between these two things. We have the field, and then we have the coil itself, and we're trying to maximize the amount of flux which is passing through that coil. So in this case, on the left hand side, this is the maximum, because you can see there's lots of field lines passing through the area. If, however, we look on the right hand side, we've got the same coil, however, it's been rotated about 90 degrees, and you can see that there's no field lines passing through the coil. If you like, the field lines are parallel to the surface that we're looking at, and so therefore this would be a position of minimum flux. In fact, this would be a position of zero flux. There are no field lines passing through the coil. Okay, so as I've said, it's a bit vague, it's a bit sort of hand wavy when we talk about flux. It's really just this idea of amounts of field, and we're going to try and formalize this in the next slide. So let's have a go at trying to make this a bit more mathematical. First thing to point out here is that when we're going to define flux, we also have to redefine one of our other variables, and that is the field strength. In the SL part of the IB physics course, you'll learn about magnetic field strength. You'll have learned that the magnetic field strength is the force per unit current per unit length on a conductor which is at 90 degrees to some field lines. Now, absolutely, that's great. However, in IB, we tend to use this in a slightly different way. We call the magnetic field strength, the magnetic flux density. And hopefully it'll become clear why we do that in a second. However, I'm just putting this up just now to know that anytime I use this word magnetic field strength, I'm also talking about a concept called magnetic flux density, which is shown as the same letter B. Okay, so we have almost two uses of magnetic field strength here. We could talk about forces, we can also talk about the flux. Why do we call it the magnetic flux density? Well, the magnetic flux, and in this case we use the symbol phi, is the product of the magnetic field strength normal to a surface and the area of that surface. So in other words, we would take the area and the magnetic field strength, multiply them together, and we get that flux. And that kind of makes sense, okay, because in that previous slide we said that magnetic flux was a measure of how much field is passing through. Well, if you look at the image at the top here, if I have a large area, then we're going to have a lot of magnetic flux, and we're going to have a lot of magnetic stuff passing through the surface. However, also if we have lots of a higher field strength, then we're going to have more lines because that'll be a stronger field, and therefore there'll be more magnetic flux passing through the object. So we're looking there at the product of the two, and that's our magnetic flux. Okay. Now, you'll notice there in my equation, I've added something else. We've got B, absolutely, magnetic flux density or magnetic field strength. We've got A, the area, okay. And then we've got this thing, cos theta. Now, this is where we have a little bit of trouble, because when we're thinking about this, obviously we looked at the previous case where we had the orientation of the two coils in different ways. We had one where they're parallel and one where we were perpendicular. Well, this leads to the idea of components. Magnetic fields are vectors, and so therefore they have direction. In the case above, if we wanted to try and find the amount of flux passing through this coil, here we can notice that there is an angle between the two. Now, obviously, what we're going to do there is we're going to take components of this one. We have a vertical component which is passing through, that's going to contribute to our flux. However, we have a horizontal component which is passing parallel, and that's not going to contribute to our flux. So what we do is we take the component of the magnetic field which is passing through the coil or the area that we're looking at, and then that's what we're interested in order to calculate our flux. Now, where this gets a bit tricky is the definition of this angle. What we do is we imagine our surface here. We then imagine a line pointing at 90 degrees, in other words, a normal to that surface. And we measure the angle between that normal and the field itself. So if you can see here, if we had a field which was vertical passing through, our theta would be 0. Our cos of theta, or cos of 0 would be 1, and we'd have just simply b times a. If, however, we thought about field lines passing parallel, then the angle would be 90 degrees. Cos of 90, I should say, is going to be 0, and therefore we have 0 flux. So that angle is measured from the normal, and that's an important part of it. We've done this when we were looking at light passing through between surfaces, for example. This is the same way. The normal is the line which is perpendicular to that surface. Okay. Here, we're going to define a couple of quantities. We've got phi, which is our magnetic flux. Now, magnetic flux is measured in Webers, if I'm trying to pronounce it correctly. This is just the unit of magnetic flux. Okay. Now, if you want to try and define what magnetic flux kind of is, or what those Webers mean, we've got our magnetic field strength, or our magnetic flux density, Tesla. We've got our area, and then we've got our angle in degrees there. So 1 Weber is going to be equal to 1 Tesla times meters squared. Again, that doesn't really necessarily help with the definitions. However, it's another way of looking at that. As if that wasn't enough definitions of stuff, we actually tend to think of and use this in a slightly different way. Often when we look at magnetic flux, we are talking about one coil of wire, for example, one loop of wire. However, in reality, and we'll see in an example question in a second, we might want to look at, say, in a solenoid, multiple coils. Okay, so we might want to look at the amount of flux going through a lot of coils, not just one. And for that, we calculate the flux linkage. Now, it's just really simple, actually. What we do, if we want to calculate the flux linkage, there's no symbol for that, weirdly. It's simply the number of turns n multiplied by the flux through one turn, which is going to be this one here, BAN cos theta. I had some students who like to remember this as NBA cos theta. They were big basketball fans. Absolutely, it doesn't matter what the order is. Okay, and those are our 4 variables. So just to reiterate here, if we wanted to get more flux through through a number of coils, through n coils, we'd change a few things. 1, we would change the field strength. 2, we would change the area of those coils. 3, we would change the number of the coils. And 4, probably the weirder one, the less straightforward one, we would look at the angle. Okay, an angle of 0 gives maximum, an angle of 90 gives 0. Take a second to digest that, add any notes you want to do, and then if you hit play, we'll look at an example in the next slide. Okay, ready to go. So let's have a, oh, whoops, sorry, I forgot to add that. N is the number of turns, okay. And then we'll look at the flux linkage here. Okay, you can see, classic example, we've got a solenoid in a magnetic field. Okay, we've got an area, we've got a magnetic field strength or a magnetic flux density, 250 turns, and quite simply all we're asked is to calculate the magnetic flux and the magnetic flux linkage. So just take a second to try that and then we'll go for it. Okay, hopefully you've had a chance to have a look at that. Okay, the way we're going to calculate this, we're going to firstly calculate the magnetic flux. Now in this case, we don't need to worry about this theta because you can see my surface, the normal to that surface is going to be in the same direction as my magnetic field, and so as a result, theta is going to be 0, cos theta is going to be 1. All we'd have to do then is use the fact that phi is equal to b times a, so this is maximum flux. We'll do 2 times 10 to the minus 3 times 0.1, okay, and then we end up with 2 times 10 to the minus 4 Webers. To get the flux linkage, all we're going to do is multiply that by the number of turns. Okay, we're going to go n times phi, we're going to multiply that 2 times 10 to the minus 4 by 250 to get 5 times 10 to the minus 2 Webers. Wonderful. I think that's where I'm going to stop. As I say, I think this concept's a bit abstract, as you'll have found when I'm explaining it. It's really hard to explain this, actually. It's a really kind of qualitative idea, which we're trying to make quantitative. What we'll do in following lessons, like I've said, is try to see why this is important and how we can use it. But for now, all you need to be confident with is how to calculate it, and we'll look at the applications of that later. As ever, thank you very much for watching. And yeah, absolutely let me know if you've got any questions about this. Bye.